Okay, physics studies, welcome to a video of me solving the problem that we looked at in class. Hopefully this is looking familiar. Basically what we've got here, of course, is a parallel plate which gives us a nice uniform electric field. I'm going to go ahead and say that this here is the positive side and this is the negative side, which gives us a nice uniform electric field like this. Okay, and then of course there's a little hole in the uniform electric field plate here, which means this, whatever we have in here, which I think we said was going to be an electron, there's my electron, it's going to be accelerated towards the positive plate. Okay, it's going to come like this, through the little hole, and then into another parallel plate which has the same voltage and the same separation distance. This time we're going to say that the positives are at the top, negatives at the bottom, and there's actually only 0.06 meters between the gap and the top plate. So this electron is going to do this, and it's going to collide with the plate. And of course we're asking the question, well, how far did it travel in the X direction, or how far along the plates was it before it hit? So, a couple of concepts here. First thing is the parallel plate accelerator. So this is the electron accelerator or the charged particle accelerator. When we switch this battery on, we connect the parallel plates, this uniform electric field is going to do work on the electron and push it this way, which means it's going to be accelerated. So given that we know something about the energies of this, we're going to give ourselves an energy, sum energy initial is equal to the sum energy final, and hopefully you can remember that the energy change is going to be an electrical thing. So this electron is going to gain energy in the form of kinetic, because it's going to end up being moved with a velocity, but that's going to come from electrical energy. And hopefully you can recall that from your data sheets, a change in electrical energy is going to be equal to VQ, and of course kinetic energy is half mv squared. So this little electron is going to be chucked out here of this little hole, and it's then going to undergo some projectile motion type of movement. Let's get this velocity first of all. This is step one. We need to know the velocity of this electron in the X direction. Okay, and we're going to get that from here. Hopefully you can recall this. This should be fairly familiar to you now. We're going to solve for the velocity. So we're going to get 2VQ upon m rooted, and that's going to give us a really large number. This is an electron that's traveling quite fast, 2.99 to 8, I think, something times 10 to the 7 meters per second. Okay, so I'm going to put that up over here just so that it's out the way. 2.99 something times 10 to the 7 meters per second. Okay, so now the electron's into the second electric field, which has the same voltage, the same separation distance. So this is now going to be undergoing some kind of projectile motion. So I'm going to be thinking about this in X and Y, and hopefully you can recall doing this from your physics 20 days. I'm going to talk about uniform velocity in the X direction and accelerated velocity or accelerated motion in the Y direction. So I have an acceleration, I have a VI, I have a VF, and I'll have a D. The D actually I know it's going to travel 0.06 meters. The VI is going to be 0. The VF I don't know, and the time I don't know. So I'm going to have to do a little analysis here of what's happening to this electron, and hopefully it's pretty clear. And again, we talked about this in class. No matter where this electron is, it's behaving just like a projectile motion on planet Earth, in that there's only one direction that the force is occurring. It's happening in the Y direction, and that's why we are using an accelerated motion formula here, whereas in the X, it's going to continue at this velocity until it hits something else, or until another force acts on it. Now, interestingly enough, we're thinking about this as on planet Earth. Why don't we put a gravity force here? Well, we don't put a gravity force here because the mass of an electron is very, very small indeed. So this, and this is given to you on your data sheet. The mass of an electron, 9.11 times 10 to the negative 31 kilograms. So we're basically ignoring gravity. So the only force acting on this is the force electric. So how do I work out the force electric? Well, I know something about the electric fields. I know that the electric field here is going to be V over D. Okay, so V over D, 30 volts divided by 0.3 meters. That's going to give me a 100 Newton per Coulomb electric field. Okay, now this electron is being placed into this field. So if I'm placing something into a field, I would be interested in a formula that looked like this. Remember from when we were looking at non-uniform electric fields, we looked at two different formulas for electric fields. One which is creating the electric field, and the other one where it's placed into an electric field. This is the one where you're placing an object into an electric field. Now I know Q, right? The Q is one elementary charge, which is 1.6 times 10 to the negative 19 coulombs. And now I actually know the electric field is 100. So the force is going to be EQ. Okay, so let's just rearrange that. Hopefully this makes sense. So one elementary charge multiplied by the electric field is going to give me my force. And of course, let's just get rid of that for now. If I have a force, I know from Newton's second law that I can solve for an acceleration, especially because I know the mass of the electron. So 100 times Q divided by the mass of an electron is going to give me the acceleration. So let's write that down. Acceleration is going to be the force electric, which is QE divided by the mass. Okay, so hopefully then when you plug that away, you get 1.756 something. I'm going to keep all my digits in here because I'm not rounding up at this point, and that is 1.756 times 10 to the 13 meters per second squared. So that's going to come over here, 1.76 times 10 to the 13 meters per second squared. Okay, so that gives me my acceleration. I know my VI, I know my distance. This means I can now solve for time. Okay, so let's do that. Actually, just quickly, we'll just pay attention to the units here. Charges in coulombs. Electric field is in newtons per coulomb, and obviously the mass is in kilograms. So we can, if we do a quick unit analysis, we should be able to check that we end up in, well, we're going to end up in newtons per kilogram here, aren't we? Because the coulombs cancel. Newtons per kilogram. Well, newtons per kilogram, hopefully you can recall from, sorry about the drilling, newtons per kilogram is the same as meters per second squared. So we're okay there, we've done our unit. Unit analysis always helps just to check you've done the right thing. Okay. Now we've got our three things. We've got acceleration, VI, D, we're solving for T. No VF. So kinematics, I'm going to use my VIT plus half AT squared. That is 0 because we are in the vertical, there is no starting velocity, which means I can solve for time here by going to D divided by A and rooted. So the time, if you plug this in, you end up getting 8.2659 times 10 to the negative 8 seconds. That's your time. That's going to come into this column here, and we're going to use this velocity, of course. So 2.99 times 10 to the 7. And now we're just going to solve for the distance, and we should get our answer. So distance is going to be velocity times time. So this times this gives us the distance that this should travel in the horizontal, which ends up being 2.47 meters. And I think that's it. Hopefully that makes sense. Let me know if I've made any mistakes. We can talk about this in the next few days. Otherwise, I highly recommend practicing. There's a couple of questions I think in your workbook. Do make sure you have a look at them, and we'll be reviewing this in class and building on this, of course, because this leads on to mass spectrometry, which includes magnetic fields. Good luck, and I'll speak to you in class.